Hello students, in this video module we are going to discuss about the properties of colloids. Hope you all have understood the preparation methods and purification methods of colloids very well. We are going to continue with the properties of colloids in this video module. The first property which we are going to discuss is color. See, the color of the sol means a colloid. If you see milk, it is white in color, but the same milk, when it is diluted and seen through a reflected light, it gives a bluish tinge to the milk. Sometimes by the transmitted light, it gives a reddish tinge to the milk. So it depends upon the type of light, whether you're viewing the colloid or seeing the colloid with a reflected light, transmitted light. Okay, it varies. For example, the color of the sky. Actually, the sky is not blue in color, but the particles of the atmosphere, the molecules of the atmosphere, which are colloids, they scatter light in all directions. In the daytime, they scatter blue light. So the sky appears blue in the daytime. In the late evenings, you could see the orange or reddish orange colored sky because they reflect those colored light in the polychromatic white light. So that is the reason they appear blue, orange as well as reddish orange. So the color of the salt generally depends on the following factors: method of preparation, wavelength of source of light, size and shape of colloidal particle, whether the observer views the reflected light or transmitted light. The next, I have combined the four of the properties of colloid in this slide: size, filtrability, diffusibility, as they are interrelated. Size. The colloidal size ranges from 1 millimicron to 1 micrometer. 1 millimicron is nothing but 1 nanometer, 10 power minus 9 meter, to 1 micrometer. Micro in the sense 10 power minus 6 meter. That means 1 to 1000 nanometer. 1 to 1000 nanometer will be the size of the colloidal particle. So the size is, the pore size of the filter paper will be large. So when they are filtered, the colloidal particles may pass through the filter paper, can be easily passing through the filter paper. So especially type of filter paper which is coated, impregnated or coated with a substance called collodion is used in the case of purification of colloids. So I recollect ultrafiltration here. See, look at the picture. Ordinary filter paper has large pore size, not useful. So it is impregnated with collodion, has small pores, and the pore size will be less than colloidal particle size. So the colloidal particle will be retained, and only the dispersion medium will filter through the filter paper, will pass through the filter paper, and then along with that impurities will go along with the dispersion medium particles. So the dispersed phase, the salt particle, remain on the filter paper. So this method, this ultrafiltration explains about the size as well as the filtrability of colloidal particle. And diffusibility. What is diffusion? Okay, that also you have discussed during the purification of colloid. When a dialyzing membrane is kept, okay, that is, a colloidal solution is taken in a dialyzing membranous bag. The particles of the colloid remain intact within the dialyzing membrane. It will not move in and out. Only the dispersion medium will move in and out. That is called as diffusibility of the colloid through a semi-permeable membrane. So like true solution can go inside the semi-permeable membrane, membranous bag, and can also come out of the bag. Whereas colloidal particles will stay inside the bag. The membrane is semi-permeable, colloidal particle size is bigger, so the membrane pore is smaller. The colloidal particles cannot come out of the membrane. So the diffusibility of colloidal particle is not feasible by the use of a semi-permeable membrane. So again that property is made use in the purification of colloids. Colloidal solutions are quite stable. They are not affected by gravity. That is the non-setting nature of colloid. This non-setting nature is explained by various other properties like Brownian movement, Helmholtz double layer, various other properties of colloids. The colloidal particle remains stable. They don't settle down. When you dissolve sand, when you just mix sand and water, the sand particles settle down. Chalk powder and water, chalk particles settle down. The particle size is bigger, that is there. But still, they settle down. But when you mix gum in water, they don't settle. So what is the reason? Pollen grain in water, they don't settle. What is the reason? That is explained by two other properties: Helmholtz double layer property, Brownian movement property can explain the non-setting nature of colloids. So colloids are not affected by gravity. Colloidal solutions are heterogeneous in nature, having two distinct phases. Again, dialysis is an example. See, the colloidal particle remain intact within the membrane, whereas the dispersion medium alone can move in and out of the membrane. What is a colloid? Dispersed phase particles are dispersed in the dispersion medium. Dispersed means spread in the dispersion medium. The particles are spread in the dispersion medium. So the dispersion medium is a true solution. It can move in and out of the membrane, being a liquid. If it is a liquid, the dispersed phase particles cannot move in and out of the membrane. Reason is it is having particles of colloidal size, which is greater than the pore size of the membrane. So dialysis, ultrafiltration explains that the dispersed phase and dispersion medium are two distinct phases. So colloidal solutions can be called as a heterogeneous solution. Here another example is also ultracentrifugation. What is an ultracentrifuge? So an interesting example can be given for this. See, when the blood is taken, the blood test, how they are done. See, for certain analysis, the whole of blood is needed. For certain analysis, only the blood plasma or blood serum is needed. How to separate blood serum? The blood cells are not needed. The blood cells should not indulge in the examination or analysis of the blood sample. They want only the plasma. How to separate plasma from the blood? The blood cells must settle down. Okay, the blood cells are actually, blood is a colloid, everyone knows it. So the blood cells are distributed, they are the dispersed phase particle. The plasma is the dispersion medium. So when it is centrifuge means the apparatus like this on the apparatus here, it is given. So it is centrifuged, the 5000 rotations per minute. 5000 rotations per minute is done at a time so that the particles will settle down, the blood cells will settle down, you can take the plasma. That is a very interesting example. And the next property is concentration and density. We already know what is concentration. So more amount of dispersed phase particles are there, it is concentrated. Less amount of dispersed solid particles are there, then it is dilute. When the concentration is more, density of the colloid is more. When the concentration is less, density is less. So they both, concentration and density, directly proportional to each other. And then colligative properties. What are colligative properties? They are properties of the solutions. See, when you take a pure solvent, when you take a solute dissolved in a solvent, here you can say in the case of a crystalloid or a colloid, the dispersed phase dissolved in a dispersion medium. Definitely when you take only dispersion medium, it will have certain set of properties. If you consider dispersion medium which is containing the dispersed phase particle, it will have a different set of properties. And the change in the properties like boiling point, freezing point, all these are exhibited by colloids. So this change in properties are termed as colligative properties. And the next characteristic property is shape of colloidal particle. It is interesting to know that colloidal particle exhibit various shapes. There are certain examples. Arsenic sulfide colloid has spherical molecules. Ferric hydroxide or sol or blue gold sol, it is also called as, it has disc or plate like molecules. You have interesting shapes in the next slide also. You just see shapes of colloids: linear, spherical, rod, cylindrical. Look at the shapes of the molecules which are there. Look at the shapes of the molecules. And next property is optical property of colloids. The important optical property of colloid is Tyndall effect. This effect, you already everyday life you are seeing this effect. See, the light passing through the slit of a window, you can see the dust particles in that light. Okay, light from the projector in a movie theater, you will be able to see the projector light, the path of the light from the projector to the screen, and you will also able to see the dust particles in the path of light. This is a very good example for Tyndall effect. That means the dust particles in air, dust particles are the dispersed phase particle, air is the dispersion medium. So dust in air, dispersed in air, is a colloid. It disperses, scatters light in all direction. This scattering of light in all direction by the colloidal particle or a Sol particle is termed as Tyndall effect. So that is very well explained by this experiment. When it is passing through the true solution, the laser beam is passed, the path of the light is not visible. When it is passed through colloidal solution, the path of the light is visible. A real life example, you just see two glasses which are kept. One is having a true solution, the right hand side one is having a true solution, the other is having a colloid, and the path of the light is visible by the help of the laser light. When the laser light is passed through both the solution, the path of the light is visible. That is called as Tyndall effect. So it is observed by Faraday, and investigations are made clear by Tyndall, so it is termed as Tyndall effect. Next property is kinetic property of colloids. Kinetic property, in the sense, it is about movement of the colloidal particle. Robert Brown observed that when the pollen grains suspended in water, he put the pollen grains in water and he observed the movement of the pollen grains under ultra microscope. These pollen grains showed a random zigzag and ceaseless movement, and this movement is called as Brownian movement. The same type of movement is exhibited by colloidal particles. You could see the video which is attached, the gray color part, where how the colloidal particle move. The reason behind this movement is the particle gets bombarded with the particles or molecules of the dispersion medium. Hence, they follow a zigzag, random, continuous movement. Look at the movement of the particle. Each particle gets bombarded by the other particle. So it is moving. So that accounts for the stability of colloids. This is how colloids are stable. They don't settle down because constantly moves due to the bombardment of the colloidal particles. Brownian movement enables us to calculate Avogadro number. To confirm kinetic theory is theory of gases. It says that whenever gas molecules gets heated up, that is, the temperature of the gas is increased, the amount of heat energy absorbed by the gas molecule gets converted to kinetic energy, and the molecule moves shows rapid movement than before, and this movement is compared to the Brownian movement of the colloidal molecules. So the movement is confirmed, the movement of the gas molecule is confirmed by the Brownian movement. And next, to understand the stability of colloids, I already told you about this. The colloidal particle don't coalesce with themselves and settle down at the bottom. They don't sediment. Reason is Brownian movement. Next property is the electrical property. You will have three properties under this. The first one is Helmholtz double layer. See the central sphere, the pink color sphere in the picture, that is your colloidal molecule, colloidal particle. It may be positively or negatively charged. Here the example is the colloidal particle. You have to consider it as a negatively charged particle. So it absorbs a layer of negative charges. Look at the blue layer of positive charges, blue layer of positive charges, and this blue layer of positive charges, it is due to preferential adsorption. That means when the particle is negatively charged, it will form a positive layer surrounded by it. So it acquires a positive charge. surrounded by it, and this layer is a stern layer, it is a fixed layer, and this positive charged layer attracts the negatively charged particles in the dispersion medium, which forms a slipping plane. That means a movable layer. There are two layers, one is a fixed layer, the next is a movable layer of the charged ions from the dispersion medium. So there exists a potential difference between the layers, which is called zeta potential, and it is explained. So it is greater in the case of fixed layer, and as the distance between the particle surface and the charged molecule, a charged particle is greater, then naturally the potential is decreased. It is called as surface potential or zeta potential. Again, this is a single particle of colloid. When it faces another particle, it will also have a layer, two layer of charges, Helmholtz double layer. The outermost layer may have negative charges, so these two particles repel each other. So as the particles nearby are having similar charges, they cannot come close and condense. Hence this helps to explain the stability of colloids. And the next property is electrophoresis. Electrophoresis in short, see, this also comes under electrical property of colloid. Under electrical property of colloid, you have three properties. One is Helmholtz double layer, the other next is electrophoresis, next one is electro osmosis. Electrophoresis is nothing but movement of dispersed phase particle or the Sol particles towards the oppositely charged electrode. See, this is the U tube, the first U tube. The blue, dark blue solution is the colloid, and the red particles are the dispersed phase particle or the Sol particle. On top, light blue, on both the stems, you have deionized water, that is water free from ions. In that deionized water dipped to platinum electrode, which is connected to positive and negative terminal of the battery. If the colloidal particles are negatively charged, the colloidal particle move towards positive electrode. That means the anions move towards anode. The cation, if they are positively charged, the cations will move towards cathode, negative electrode. Here in this picture, the second U tube, you see the colloidal particle assembled, or means approaching towards the positive side of the electrode, which explains that the particles are negatively charged. So in one year question paper, it is asked how the charge of this Sol particle is determined. So they don't ask explain electrophoresis as a direct question. They asked how the charge on the colloidal particle is determined. So you have to explain electrophoresis for that. So what is electrophoresis? The migration of Sol particles under the influence of electric field is called electrophoresis. It's also called cataphoresis. So this can be asked in 2 marks as well. So if the Sol particle migrate to the cathode, they possess positive charge. If the Sol particle migrate towards anode, they possess negative charge. Thus the direction of migration of Sol particle, we can determine the charge of the Sol particle. Hence electrophoresis is used for a detection of or presence of charges on the Sol particles. You have many Sol particles, the positive and negatively charged colloids. Examples given in your textbook. You can see your textbook for the examples. And next property is electro osmosis. See, you already know that colloids contain two medium. One is dispersed phase, the next is dispersion medium. If the dispersed phase molecules are moving towards oppositely charged electrode, the movement of dispersed phase particles towards oppositely charged electrode is electrophoresis. The migration of dispersion medium particle towards oppositely charged electrode is electro osmosis. For that, we need to make the colloidal particles stay in the same place. We should create space for the dispersion medium to move towards the electrode. How it is possible? You know it. It is done by the help of semi-permeable membrane. Look at the picture. In the middle region, you have the Sol. Sol means colloid. So, on the two sides, the dotted line which compartmentalize the whole setup, they are semi-permeable membrane. So the colloidal particles stay inside, whereas the dispersion medium can move towards both sides as they are true solution particle size. So under the influence of electric field, see, look at the left hand side, you are disconnected to positive electrode, right hand side negative electrode. So when the dispersion medium particles When they are positively charged, they move towards negative electrode. When they are negatively charged, they move towards positive electrode. Colloidal particle will also try to move, but they cannot move because they are segregated by semi-permeable membrane. So same dialysis method, the dialytic membrane is made as a choice in order to understand electro osmosis. So movement of dispersion medium under the influence of electric potential is called electro osmosis. Next, coagulation or precipitation. So then what is how can we precipitate a colloid? See, milk is from milk paneer is prepared. How paneer is prepared? Only the milk particles precipitate. You can take out the precipitate, remove, filter it, and the precipitate is taken and total moisture is removed. You get paneer. I already told you about blood, how the plasma is separated. All these are coagulation or precipitation. That is, the dispersed phase particles join and they settle down. There are two types. They can form a creamy layer on top. They can form a sediment at the bottom. And flocculation, they form lumps. See, the curdled milk, they will not settle down at the bottom. They form lumps here and throughout the solution. So like that, different types of precipitation is possible. I told you creaming, sedimentation, flocculation. Okay, like that different types are possible. The flocculation and settling down of colloidal particles is called coagulation. So it is done by various methods. Addition of electrolyte, electrophoresis. How milk is curdled? By squeezing a lime. Half lime is enough to precipitate half liter milk. So it is squeezed, and while it is boiling, the temperature is increased. So only it is said that boiling. Electrophoresis. See, the particles are moving towards respective electrode. No, colloidal particles are moving, so they get neutralized at the electrode. So naturally, you can able to separate the particle. Mixing of oppositely charged sol. See, one sol is containing positive charged colloidal particle. Another sol is containing negatively charged colloidal particle. Mix both. What will you get? The positive and negative charges combine. Naturally, it will precipitate. So all these are given as example. In addition of electrolyte, you have to note this point. When the valency of ion is high, that means you are adding the ions. When the valency of ion is high, the precipitation power is also high. The ability to precipitate is also high. Okay, here Al3 plus has more ability than barium 2 plus, which has more ability than Na plus. Similarly, for the negative ion is also given. Okay, and then coagulation or precipitation. Electrophoresis. The same thing, coagulation or precipitation. Next method, electrophoresis. I already told you about the method. The charged particles migrate to the electrode, and due to neutralization, the colloidal particles can be discharged and collected, precipitated by mixing two oppositely charged salts, by boiling. Due to increased temperature is increased, number of collisions will increase. The colloidal molecules collide with each other. The collisions number will increase. Naturally, they form or they combine and settle down. Protective action. Generally, lyophobic salts are precipitated readily even with small amount of electrolytes. What are lyophobic? The no affinity between the dispersed phase and dispersion medium. Lyophilic, more affinity between the dispersed. So it is when the dispersed phase and dispersion medium has more affinity, it is naturally difficult to precipitate. It is a stable colloid. When there is less affinity for the dispersion medium by the dispersed phase particle, it can be precipitated easily. But you have to avoid precipitation for a lyophobic salt. What must we do? We should add a reagent, a protective reagent, which make the colloidal particle disperse throughout the medium, and it accounts for the stability of those lyophobic colloids. Example, a small amount of gelatin salt is added to gold salt to protect the gold salt. Zsigmondy introduced the term gold number. See, when you are taking a hydrophilic colloid, hydrophilic means water loving colloid, that will just prevent the precipitation of 10 ml of gold salt, and the addition of 1 ml of 10% sodium chloride solution. Tricky to understand, you understand it clearly. 10 ml gold sol you are taking, you are going to precipitate the gold, or in order to precipitate gold, 10% sodium chloride solution is added. But if you want to suddenly avoid the precipitation, if you add a hydrophilic colloid to it, the gold sol is protected. So how much quantity or milligram quantity of the hydrophilic colloid must be added to such a gold sol? That is your protective power, that is called gold number. See, when gelatin is going to be added with 10 ml gold sol, the gold number, that means 0.0052 to 1 milligram of gelatin, if it is added, that is enough to protect the colloid. Like that, egg albumin, gum arabic, potato starch, each one has their own gold number value. I hope you understood all the video slides, all the explanation given clearly. Thank you, children. See you again in the next video module.